Imagine a life without watching videos or listening to your favorite music or podcasts online or uploading your photos on social media. A life without Wi Fi and even your cell phone.
No, I don't want to imagine that.
All this would not have been possible without that one numerical algorithm that transformed technology, the fast Fourier transform. At the very root of this algorithm lies a bunch of complex numbers expressed as complex exponentials. Today, let's find out what these special complex exponentials are.
Hmm.
By now, we have understood that a complex exponential represents the idea of rotation. If you're confused about this, I recommend you check out the previous videos. Okay, now where is w squared?
Well, squaring means rotating the unit vector on the real line twice by theta.
Good. How about w cubed?
Rotate once again by theta.
Right. So we could keep going like this. So what we have essentially done here is to divide the unit circle into 6 equal sectors. Now what is theta?
We are dividing 360 degrees or 2 pi radians into 6 parts. So 2 pi by 6.
Exactly. So in general, the vectors e raised to j 2 pi by nk divide the unit circle into n equal parts.
Hmm.
Alright. Now where is w power 7?
Um, hey, it's the same as w. And w power 8 is the same as w squared. Oh, what's up with this?
So the important point to note here is that no matter how many full circles I draw from a point, I reach the same point. This means that two vectors are the same if they are an integer multiple of 2 pi radians apart. So a single complex number has multiple representations using complex exponentials.
Multiple complications, you mean?
No, it's super handy. This is why w and its seventh power are the same.
Hmm. Hey, that's weird.
What?
We raised a number to its sixth power and ended up with 1. And w is not even equal to 1. That's weird.
Right. Let me show you something weirder.
Okay.
Now w power 6 equals 1 says that when you rotate by the angle theta 6 times, you reach 1. Now what happens if you take the sixth power of this vector?
Okay. This is its first power. Second, third, fourth, fifth, and sixth. Oh, we reached 1 again.
Yep. Choose any of these vectors and raise them to their sixth power. You'll see that they all reach 1.
Really?
Yep. Check for yourself.
No wonder these numbers are called complex numbers.
So we now have a bunch of complex numbers which when raised to their nth power yields 1. Therefore these numbers are the nth roots of 1 on the complex plane.
Oh, in the real line, we just have two options for this. Interesting.
Yeah, exactly. So finding the nth roots of unity now looks like a cake cutting problem.
Or pizza.
Yeah.
But wait, what if we just rotate the whole thing? Are these the roots of some other complex number? And what if I scale them all? Does this mean anything significant?
Good questions. To answer them, let's now try to find the nth roots of a generic complex number. So we now need vectors which when multiplied n times give us r e power j phi. In other words, what are the vectors which when scaled and rotated n times in a sequence reach the desired point on the complex plane? I really like how a question of finding the nth roots of a complex number is all about n number of equal rotations on the complex plane. Anyway, we can calculate r0 as the nth root of r. Next is this term. We need to find theta. Now the vector e power j phi by n becomes quite obvious since rotating it counterclockwise n times would lead us to e power j phi.
Okay, what about the other n minus 1 roots?
Here, this fact comes in handy. So we now have this equation from which we get the angles of the roots. Since we need n of them, let's take any n consecutive values of k.
What about the rest of k?
Hold on, you'll see. Note that when k equals 0, we get e power j phi by n as one root. So we have this equation before us. This expression means that we first divide the unit circle into n equal sectors and then rotate them all by an angle of phi by n. Scaling these vectors by the nth root of r, we get the nth roots of the complex number r e power j phi. Now let's find the cube roots of minus 1. We first divide the unit circle into 3 equal sectors and then rotate these vectors by 60 degrees. These are the cube roots of minus 1. To convince ourselves that these are indeed correct, let's cube these roots. 1, 2 and 3. We see that all the roots reach minus 1 when cubed.
Cool, but what about the other options for k? It can take any integer value, right?
That's right. But because of this property, we see that for other values of k, the roots merely repeat. So yeah, we see that by suitably rotating and scaling the nth roots of 1, we can get the nth roots of any complex number. How cool is that? Now the nth roots of unity on the complex plane constitute a crucial set of numbers central to our technology-driven lives.
Wait, are you trying to tell me that without the nth roots of 1, I wouldn't be able to connect my cell phone to the Wi-Fi?
And you're trying to tell me that you have a cell phone?
Hey!
Just kidding. But yeah, that's true. These roots of 1 sit inside what is called the Fourier matrix. And the fast Fourier transform gives us clever ways to make computations with this matrix. And such computations are necessary to develop a lot of technologies.
Oh.
We'll discuss all this later on in detail, but for now, let's continue building the necessary mathematical foundations so that you can truly appreciate the technologies we have built. So yeah, see you in the next one.